So if I'm here, just, standing still here, observing things in the world, I can measure how far things are away from me right now. Like there's this sort of remains of a tree that I'm putting my camera on right here. I can measure how far away that is from me. I can measure the speed at which someone is moving relative to me. They're walking by or running by. I can do all that. I can observe the world around me. And I can explain all that motion, all those positions, all that motion with all Newton's laws of motion, all the laws of motion that we know and love. And so if somebody is running past me, I can observe their speed, let's call it v, relative to me. They're just moving at a speed v relative to me. That's all normal, that all makes sense. And I could also be moving also relative to the earth. So before I was just still relative to the earth, and now I could walk relative to the earth, or sort of jog a little bit relative to the earth. And then I can observe things as well in this frame of reference, or this point of view. I can observe people walking past me. I can observe the position of objects relative to me, like this remains of a tree here. As I'm moving with a speed v this way, that tree, the remains of a tree, is moving with speed v, but in the opposite direction. Obviously that makes sense. We're all familiar with that. As we move forward, things move behind us. But again, all that makes sense with Newton's laws of motion. If I'm moving with a speed v in this direction, and then somebody else is also moving with a speed of 2v in this direction, I will observe them moving at a speed relative to me of v. That's 2v minus v. And that's just simple, they call it Galilean relativity. And I should note how these sort of points of view, me just standing here or me moving at some constant speed, those are sort of points of view, or the more sciencey term is frames of reference. And so I am observing the world through this frame of reference. I would also have, and this is more a sciencey term, a coordinate system that I measure things, where that coordinate system is relative to me. So if I'm moving at a speed, I observe and measure things relative to me with a coordinate system that is centered on me. And of course you can be in one of these frames of reference, like a train or a car or a plane or something like that. And those are called inertial frames of reference, because I can explain all the motion that I see in that frame of reference, in that point of view, with Newton's laws of motion, all the laws of motion, and it makes total sense to me. And I can make this more advanced as well. What if I start to accelerate? What if I were to accelerate forward? Accelerate this way. Kind of hard to show that. Me just accelerating. If I accelerate at a constant acceleration, what would that be like? That would also be a frame of reference, a point of view. I could observe things while I'm accelerating. I could observe things moving past me. The whole world's going to move past me, and I can observe all those things. But this is a distinctly different situation than the inertial frames of reference that I just showed you, where I'm moving at a constant velocity. If I'm accelerating this way, say at an acceleration of a, I see the rest of the world around me accelerate at minus a. I can say that, say an object, this remains of a tree here, is moving past me at an acceleration of minus a, and it's almost like there's a force on this tree with a magnitude of its mass times the acceleration that I'm observing it moving at. So it's almost like there's a force, but it's not really like a real force. It's sort of fictitious. It's not really real, but it can be very useful. I could use that force and the acceleration I observe to, model how it's moving through space. And also I should note, there could be other forces, on this tree trunk if it were moving through space, or if there's like friction and air resistance or something. I mean, it's a tree trunk, so it's not moving anywhere. Let's say if there were, then I could add all those forces together, including this apparent fake force, its mass times the apparent acceleration that I get from just moving. I could add all those forces up, and I could just set that equal to its mass times its total acceleration. That's just Newton's second law, that F equals ma. The force on an object equals its mass times its acceleration. But I'm getting a little off track, a little ahead of myself. The point here is that me moving at an acceleration, me just moving linearly forward with an acceleration, and me observing things around me, that is called a non-inertial frame of reference. Because if I don't have any context of whether I'm accelerating or not, if I were in a big train and I didn't know that it was accelerating, or I was in some object I know it's accelerating, it's a train. If I was in some object and I really had no idea that it was accelerating, I would see objects move past me. And I'm going to explain this more later on in the video. But I would see objects move past me and I would have no context for the acceleration. I would have no idea that I was accelerating. Here, I know that I'm accelerating because I am the one accelerating. But in that example, I wouldn't know. And so I would have to come up with these fake fictitious forces to describe the motion around me. And that's a non-inertial reference frame. When there's accelerations and I have to use these fictitious forces to explain the motion around me. Okay, so now I'm going to talk more about inertial and non-inertial frames of reference and explain it a little better with a good example. And I'll talk a bit more about how these fictitious forces arise in accelerating frames of reference. So now I pass it along to myself in a much warmer environment. In accelerated frames of reference, you have to introduce fictitious fake forces in order to explain the motion that you see. The motion that you observe is actually pretty interesting because in your point of view, you're not moving at all. Your surroundings aren't moving at all. If you can't see outside, you have no idea that the capsule you're in or whatever is accelerating. So from your point of view, you're not moving anywhere. And then all of a sudden you have a block of ice on your table start moving in a particular direction. Now, if you were outside, you would know that, well, obviously the car that this person's in is decelerating, and so it makes sense that the ice cube would be moving. But in your reference frame connected to that accelerating reference frame, an ice cube doesn't just start moving without a force acting upon it, an external force. And so there has to be a force. So you have to introduce like a fictitious or fake force to describe the motion of this ice cube. Not like the fundamental forces of nature like gravity, electromagnetism, and the strong and weak nuclear forces. It doesn't follow Newton's third law because Newton's third law says that for every action, for every force, there's an equal and opposite force. So if there's a force that acts on the ice cube, well, you would expect that if that's a normal force, and not a normal force, that's a whole different thing, but a typical force, then there's something else in the universe that should feel an opposite force. This even applies in rotating frames of reference. For instance, the Earth. Or let's focus on something more simple, let's say like a turntable or like a carousel. If the carousel goes fast enough and you're holding on for your life, you're going to feel this sort of apparent outward force pointing outward. And if it goes fast enough, it would be kind of hard to hold on. And this even applies to on the Earth as well. The Earth is rotating about an axis through the poles. And so there is some motion that you could observe on Earth that you can only explain by introducing fake, fictitious forces. And you may have heard of some of these, like the centrifugal force or the Coriolis force. And rotations are considered accelerated frames of reference because you're always being accelerated inward. There's a centripetal acceleration inward in order for you, if you're in this frame of reference, to even be rotating at all. I find it really interesting because in order to explain the motion, you have to introduce these seemingly real forces, but really they are just an aspect of inertia. But they appear real. These fictitious forces are incredibly important because they affect things as big as hurricanes and air currents and water currents, and pilots on planes have to take it into account because of how air currents and winds change. Storms and stripes on Jupiter and the Great Red Spot and storms and air currents on other planets are dominated by the Coriolis force. So I'm going to show an example here. I want to make it clear what inertial and non-inertial reference frames are. And so it should be pretty clear from this example. So let's say, and this is all linear, no rotations yet. So imagine that you are in an igloo, right? Because, that's relatable. And this igloo is on ice. Just imagine that it's like essentially frictionless, just imagine frictionless. It's an igloo on ice. I mean, I don't know. And so it's moving at a constant speed at a velocity of v0. And you, observer, are right here. You are the stick figure person here. And then you have a friend, a buddy, that is outside. And they are stationary on the ground. So they aren't moving at all. And they are following a coordinate system like this, where z is going up and x is going to the right, and this is fixed to the earth. There's ice in the igloo too. I mean, it's an igloo, ice everywhere, ice galore. And then you have a table, which is also made of ice. And this table has a block of ice, just a cube of ice on it, as you can see right here. And so, and this cube of ice is just sitting still, and this whole thing is moving to the right at speed of v naught, v0. You are following this coordinate system, and this coordinate system is fixed to this igloo. So as this igloo moves, this coordinate system moves along with it. Now, let's just say that this igloo starts to slow down. Maybe it hits a rough patch in the ice, or I don't know, there's rockets on the side. I don't know, something that, whatever it is, something that causes it to decelerate. So it starts accelerating in this negative x direction. So it starts slowing down. What you'll see in either case is you'll see, so you or your friend will both see this ice cube will start to slip to the right relative to the igloo. So the whole igloo is going to slow down. But this ice cube is not, firmly attached to the igloo because this is frictionless below it. Before it starts to accelerate, the igloo has a momentum of its mass, it's called big M, times v naught. And this ice cube, it has a mass of like little m. It has a momentum of m, little m, times v0. But you're slowing down the igloo, so the igloo's momentum is going to get a little less, it's going to get a little slower. But this ice cube still has its same momentum. And so it's going to continue with the same momentum that it had in the beginning, which is going to cause it to appear to move forward relative to the igloo. So to your buddy, to your friend outside, they will look and everything will look pretty normal. They know that the igloo is slowing down and it's going to move relative to the igloo because the igloo is slowing down and the ice cube's not. So that all makes sense to your friend observer out there. But you are inside the igloo with your point of view and your coordinate system fixed. And so you have no idea that you're even moving at a speed of v0. But the igloo starts to decelerate. And then this ice cube starts to move. In your point of view, you don't have the context of the igloo moving at a speed v naught relative to the Earth. Because for all you know, your whole igloo, this is your world. And it's not moving anywhere. It's stationary to you. Even if you're moving, this is all you see inside the igloo. And so all of a sudden you see this ice cube moving. And the only way for you to explain that is if you say, there must be a force. For something to move from rest, there has to be a force there. And so you think, well, there must be a force because the room I'm in, according to you, isn't moving, isn't accelerating. So in order for Newton's first law of inertia to hold, and in order for this motion to make sense to you, you think you have to introduce a force. You have to call this, the push force or whatever, the mysterious push force that's pushing the ice cube to the side. And you could give it a name, you could even quantify it. Whatever the acceleration is of this igloo, you can multiply that acceleration by the mass of this ice cube, and that is your force. It's sort of a force. It's like a pseudo force. You can do some math to describe the motion of this ice cube just fine. So it's a useful sort of construct to invent a fake force, even if it's not really real. It's just an aspect of inertia. But in saying there's a force, you can actually use it in math and physics, and you can actually do stuff with it. There's going to be a lot of fictitious forces, fake forces that pop up that you can invent, that you can use, that we have used in the past, that aren't really real forces, but they are very, very useful, as mathematical equations in physics to, be able to describe the things that are happening on Earth in order to understand the motions of certain things on Earth. So the point here is that you, in your frame of reference here, you are in a non-inertial frame of reference or an accelerated frame. And your person outside, they are in an inertial frame of reference. Inertial because they can explain all the motion that they see with the laws of motion from Newton. Newton's first law, second law, third law, they can all explain it. It all makes sense. They don't have to introduce any fake forces in order to explain the motion. It's inertial. You can explain everything with just inertia. But the person inside here, you, they can't do that. They have to introduce these fake forces. They can't just use inertia in order to explain the motion that they see. Hence, non-inertial. So here you can see what appears to be a dodecagon. It's just a 10-sided polygon. And it appears to be still. I've sort of green screened out the background, so it's just a dodecagon, and it appears to be still and not moving. But in reality, and it can be hard to tell, but this dodecagon is actually rotating. It's rotating around, and I can show you my setup as well. It is rotating around, but it doesn't look that way. It actually is very hard to tell, and if I were perfect in my setup, you wouldn't be able to tell. You wouldn't be able to tell because as long as the camera and the object I'm recording that I'm interested in is fixed to this rotating frame of reference, then you shouldn't be able to tell at all just by watching this video that they are in a rotating frame of reference. And I can also show in the case of this umbrella where I attached my camera to an umbrella and I just let it spin, and you can tell that it's really hard to tell, or even impossible to tell, that it's in a rotating frame of reference. Obviously, you know, my setup wasn't perfect and there's some shakiness, so you can kind of tell. But if I got rid of that, it would be pretty much impossible to tell. That just goes to show how it can be difficult to tell if you're in an accelerating frame of reference, especially in a rotational one. But of course, I should say, there's a caveat here, is that, well, it's not a trick, but it's very simple because there's nothing in the frame that is able to move. You know, if there was a ball that was able to roll across this umbrella, you would be able to tell that there are actually these apparent fictitious forces arising. It appears that there's forces acting on this ball, that it moves in a way that's very unnatural. It doesn't seem normal. At least if you were in an inertial reference frame, just me rolling a ball, it would look very unnatural. But if I were to show an object moving in that frame, you'd probably be able to tell pretty easily that you were in a frame of reference if you were in the know about, you know, what to look out for in rotational frames of reference. For instance, you'd see like the centrifugal force and the Coriolis force. Those are two apparent fictitious forces that you may observe in rotational frames of reference like these. So the point is, it can be hard to tell if you're in a rotational frame of reference, but if you know what to look for and you're looking at how objects move in this frame of reference, then you can tell. If you're careful about your measurements, if the rotation speed is small enough, then you still can tell. And if the rotation speed is really high, that makes it easier to tell, because then the observed, you know, fake forces, the weird motion, is more prominent. Now, I'm not going to talk about this in this video because the video is going to get long enough already, but this relates directly to things like the Earth, because the Earth is a rotational, accelerating frame of reference, and there are actually fictitious forces that you can observe. You may have heard these before. The centrifugal force and the Coriolis force are fictitious forces that you can observe on the Earth if you're careful in looking for them, and sometimes not careful at all. Some are very prominent on the Earth, and so I just want to sort of allude to that here, but I will get to that in a future video. Imagine there's a camera, you were on the edge of a turntable, or let's say you're at the end of a carousel holding on, and then you're moving around. So that would be a non-inertial reference frame because you're rotating around. Your frame of reference is rotating relative to the fixed frame of reference of like something on the outside that's not moving. So to make it clear, the person standing on the outside, that is the inertial frame, because they can explain all the motion with the laws of motion and the law of inertia. They can explain all that, no worries. But then the person or the camera in the rotating frame of reference, that is the non-inertial frame, because they can't explain the motion that they see just with the law of inertia. They have to introduce those fictitious forces. Therefore, this is the non-inertial frame. This is the inertial frame, or the accelerating frame. So right now, I am moving at you at some speed, and you're moving at me with that same speed. And we are in an inertial frame of reference. Although I did say the Earth was rotating, and that is true. So really, we are technically in a non-inertial frame of reference because the Earth is rotating and we are constantly accelerating. But because of Earth's relatively small rotation given its size, the magnitude of those forces, those fictitious forces on us, are pretty small. So it's a very good approximation for me to say while I'm walking at you that is an inertial frame of reference. But if I were to move faster, if I were to shoot a cannonball or do something crazy, or if I were to look at, you know, huge air currents, I would notice that those fictitious forces are no longer, you know, able to be neglected. They are actually quite large. So it's a very good approximation to say that we're in an inertial frame of reference. But technically, if you want to be exact about things, we are in a non-inertial frame of reference. Okay, so thank you for watching. That's all I have for this video. If you enjoyed this video, I would appreciate it if you subscribed, if that's something you want to do. I plan on making more videos on this topic. Those may or may not be out by the time you watch this, but I recommend subscribing so you can stick around if you found this video interesting and you want to see more. I barely scratched the surface of this topic of relative motion and accelerating frames, as there's so much more to talk about and so much more to go into. If you liked the video, I'd appreciate it if you gave it a like as well. That would help me out. And yeah, that's all I have. And yeah, I should probably go back inside because, you know, it's snowing and my camera's getting wet. So I should probably stop. Bye-bye.